Okay, so hi PyCon, I'm Edd Barrett, and today I'm going to talk a bit about some research that we're doing at King's College London within my team, which is the software development team. This is my usual team, these being in the black and white area. So the name of the game for us is language composition. So what I'm basically going to do in this talk is talk about really what that actually is and why we might want it. I'm going to discuss some of the challenges which face us when doing proper language composition. I'm going to describe an approach which we believe overcomes these challenges. And then finally, I'll show you a composition which I've written on PHP and Python. And this will concretize the ideas, and I'll show you some experimental results. So let's jump right in and first begin talking about what we mean by language composition. So a loose definition would be the ability to write a computer program in a mixture of programming languages. So, for example, you could have a program which is written in, say, Ruby and any other language you can think of off the top of your head. So why may that be useful? Well, the most obvious reason is that different parts of programs are often better suited to certain programming languages. And that may be for reasons of expressivity, or it may be for reasons of performance. However, a second reason why you might like to use language composition is to migrate a system from one language to another. So if you have a large code base which is implemented in a legacy programming language, you may wish to move it to something more modern. Now, one approach to do so is to rewrite the entire thing from scratch, and it could take you 10 years, it could take you 20 years, it could take you however long it's going to take you. What you could do instead is use language composition to move parts of your program from one language to the next, the whole time leaving your code base executable. It means you don't have to do that clean room rewrite. So that motivates language composition. There's probably people in the audience now thinking, well, we already have language composition in the form of FFIs. The FFI is foreign function interface, and a very good one for Python is CFFI. Now, whilst there is a language composition, I'm going to argue that this is a limited form of language composition. So let's see if I can convince you of that. So your typical architecture for an FFI looks like this. You have on one side a high-level programming language, and you're usually calling down to something lower level like C or System ABI or the implementation language of the higher level language. But anyway, you can call down and return values come back. So the first thing that annoys me about this architecture is, why does it have to be a high level language and a low level language? Can these be any language? That would be nice. The second thing is that notice that these two source codes are in separate files. Now, wouldn't it be nice if we could sort of lift that barrier and interlace our different languages within one file? Because if we could do that, then we have the ability to do some more intricate interactions between the languages. Perhaps it would be possible to mix from these different languages modules, functions, methods, expressions, or even scripts. So that's really the dream of language composition that we're trying to kind of achieve. But of course, the whole time, we have to think about performance. Because if language composition slows down users' programs, they just aren't going to adopt our composed VMs, and it renders the whole thing pointless. So really what we want is fine-grained language compositions. By fine-grained, I mean very high levels of interoperability, and we also need them to be fast. And the question is, how do we do this? So let's drill deeper. Suppose that we have two programming languages, X and Y, and we wish to compose them to build a composed VM, which we're just going to call programming language instead. Well, if we look closer, there are two discrete aspects of these sorts of programming languages which themselves need to be composed. And these are the syntax and the runtime. So let's delve a little deeper, start looking at what it would mean to compose syntax. So, programming language syntax is described by what's called a grammar. So what you can imagine doing is taking two grammars, somehow joining them, and then building a new programming language grammar. And the question is that easy? Well, as it happens, it's really not easy. It's completely non-trivial. Without going into too much detail, no matter what parsing algorithm you use, you're going to face problems. And these are, I'm going to find this shadowing ambiguity. Like I say, I'm not going to go into this stuff. So people started looking for ways of sidestepping the parser altogether to achieve language composition. One approach is called syntax-directed editing. Anyone heard that, by the way? Yeah, well, that's cool. Okay, so The idea behind syntax editing is that the user is forced to edit the AST instead of text. The AST is the abstract syntax tree. It's the view on the program from the compiler's point of view. Now the problem with such an approach is that it's almost like coding by numbers. You don't have the free-form text editing experience that we've all come to know and love. You cannot make mistakes. You can, basically, the thing has to be in AST the whole time. And for this reason, it hasn't been adopted as a feasible way of editing programs. So at this point, I'm going to say syntax composition is actually a barrier for proper language composition. So that's annoying, but what about runtime composition? Is it easy to take two runtimes and compose them? Well, we actually wrote a paper on exactly this. We took some interpreters implemented in different ways, and we composed them, and we looked at the results. So the easiest way to compose interpreters is to take two simple interpreters written in a language like C or C++, and then write an interfacing layer which glues the languages together and offers cross-language interfaces. Now, that works functionally, however, it tends to be slow. And the reason for this is that C interpreters tend to be slow in isolation. So if you put two C interpreters together, you don't end up with something fast, and that's probably no surprise to anyone in this room. So what can we do to try and claw back some performance? Well, what we can do is we can use just-in-time compilers. Now, just-in-time compilers are very intricate systems which take multiple decades in some cases. And for this reason, I'm going to say this is too much engineering effort. Some languages never get as far as getting into it, and here we need two languages for JIT. So what we could try doing instead is being a bit more crafty and implementing the languages on top of a VM which already has a just-in-time compiler, such as a JVM. Now sadly, whilst that looks like it should work, it doesn't always perform well. Dynamic languages have a very tough time running on the JVM. So we want something more general that's going to work for all programming languages, basically. So that brings us to our second barrier, runtime composition. So we have these two problems, we need to tackle them. What are we going to do? So our idea is to use two new technologies. One is called language boxes and one is called meta tracing. Let's describe these in a bit more detail. The idea behind language boxes is that we borrow the idea of editing the AST from syntax editing, but we try and give back to the user that palatable editing experience, the text editor field. But by doing so anyway, we can compose our grams without annoying the user so much. Here's an example of how this kind of thing might work. Suppose that we're editing some Java code, and we're going to iterate over some result set from a database. Using language composition with language boxes, what we would do is we first begin typing our Java code. So we just type for string, for a string is colon, nothing unusual there. At this point, the user can use a special key combination to drop into a SQL language box. At this point, the user then types free-form text into the language box. And just as we drop into an SQL language box, we can then drop into a Java language box in the SQL language box, if we so wish. Now, what I want to take away from this is that, one, we didn't annoy the user too much. There was nothing really new for them there, other than they have to use a key combination to change languages. But secondly, these are all the boxes are parsed independently of the others, which means that we don't end up with the problems I showed you in the earlier slide, ambiguity, shadowing, etc. All the grammars know is where another language can appear, and they don't look any further. And that's how we work around that problem. So let's deal with syntactic composition. How about runtime composition? Well, I mentioned that we're going to use meta tracing. So the idea behind meta tracing, it's basically the next logical step from the tracing JIT, tracing just-in-time compiler, sorry. The idea is that you write an interpreter in a meta tracing language, you pass it through a toolchain, which you can think of as a compiler, and then what drops out the other side is a VM containing the interpreter, but also a tracing JIT. This is hugely practical, because the tracing JIT just dropped out for free. That's the bit that takes 10 years to implement. Here we didn't provide the JIT, we just described the interpreter, the JIT comes for free. And as it happens, this is exactly how PyPy works. This is exactly the architecture behind PyPy. They write the interpreter in RPython, which is their meta tracing language. It's probably the only existing meta tracing language at the moment, actually. But anyway, when you translate Python, what you do is you end up with a VM containing the interpreter and the tracing kit. Right, so that's meta tracing. But you're now asking, what does this have to do with language composition? So here is our idea. We take two interpreters written in RPython, we glue them together with glue written in RPython, and we pass that through RPython. So what we should get out at the end is a composed VM consisting of an interpreter and a tracing kit, which is now aware of how to trace across languages. So it doesn't see the two languages, it just sees one language really. It doesn't know about the difference. So through this, we basically get high performance, but with very little engineering effort. So that should deal with runtime composition. So now that you understand the methodology we're using here, let's go a bit more concrete, and I'll show you a composition I've been working on. I call it PyPy. It's a composition of Python and PHP. Its architecture looks like this. So on the left we have PyPy. I don't really need to introduce that conference like Python. PPVM on the other hand, I do. So PPVM, did anyone hear of PPVM? Oh, it's more popular than I thought. Okay, so this is a PHP interpreter written in RPython. It was an experiment to see whether we could implement PHP and get the performance benefits like we saw in PyPy basically. Then we have our glue layer here, which provides the cross-language interfaces between languages. And of course, we have to use a language box in it, so we can't parse the two things at once. So what can we do in this language? We have all of our usual FFI-like features that you'd expect to see. So you can import Python modules into PHP, you can call functions between the languages, and there's a type conversion layer much reminiscent of that in Python, if anyone's worked with Python before. So there's no surprises there. This is where it gets interesting. We have these more advanced features, so you can put your functions from the different languages in the same file. So that's like interleaving, like I showed you on the earlier slides. You can have Python expressions in PHP. You can embed Python methods inside PHP classes. We add support for references to Python so that Python can interact with PHP code which uses references. We have cross-language scoping, and for debugging purposes, we have backtraces which are aware of the two different types of languages. I'm going to do a demo, and hopefully this is not going to go wrong. You know what demos are about. I was kind of hoping I'll be facing towards the audience as well, so I apologize, I'm going to be sat side on. Okay, so this is our language box editor, it's called Eco, and on first impressions, it looks just like a normal text editor in which we can execute PHP programs. So you see the output down here in the console. That's not particularly interesting. So what I'm going to do is I'm going to press Ctrl-L, and I see here a list of language boxes which I can now enter into. So what I'm going to do is I'm going to choose the first one, which is a PHP box, and I'm going to define a Python function, which does nothing particularly interesting. It's just going to return x plus 1 for now. I press Ctrl-Shift-L to come out of that language box, and then I can call the function in PHP as though it were a normal PHP function. So I'm going to call it with 6 and 6. That's why I stop number ranges. So here we see that it can be high 6, 6, 7. So what happened was 666 was passed to this function here. The PHP integer was converted to a Python integer. The computations here happen just as they would in Python normally. The return value is converted back to Python, and then PHP knows no better. It just carries on doing its thing. So let's demonstrate a few more things. I'm going to put a variable here, which is value 555, and I'm just going to add a here. So that demonstrates cross-language scoping, since it had to look into the parent language in order to see that A was there. Okay? I mean, we can even do things like if I put this as a function in the function, will this work? I hope it works. I'm going to return a G or an H, of course. Yeah. That's the function. Now, of course, it's a closure instance, it's calling right in PHP. Will I get it right? What have I done wrong?
The 666 has to go to F.
Say again?
The number has to go into F, not H.
Yes, you're right. Demos never goes completely smooth. We all know that. There we go. So what happened there was we generated a Python function. We then returned it to PHP. PHP saw it as a callable instance. We called it, it didn't know any better, it just saw it as a normal project. One more example. So this is a slightly larger example. This is a larger example where it's a random number generator written in mostly PHP. The main meat of the implementation is here. So, basically we wanted a way of generating X random numbers rather than just one. And Python generators are a very nice way of doing this. So what we've done here is we've embedded a Python method inside the PHP class, which uses the yield statement to make a generator. Then later on, we use a list comprehension as a Python expression that comes to generator. So we get more solutions. So I can just show you how that works. Okay, so there's a sequence of random numbers. Right. Now it works. Kind of. So just a few comments on effort levels now. So implementing what I've just shown you actually wasn't particularly difficult. Our Python is quite expressive. However, deciding what the right behaviors should be is incredibly difficult. Because you want something which makes sense to the user, but it's also possible given the constraints of the languages. So basically you have to make compromises. And the question then is how bad is the compromise? I'm going to show you the most annoying compromise I had to make with that here. Collection types between these two languages are just, there's a complete disparity. To understand why that's a problem, we need to look at the conversion layer. So I mentioned that the types are converted as they pass between the two languages. So the insular strings is obvious what should happen there. For objects, we do what Python does, which is when I pass a PHP object to Python, it gets a wrapper put around the object. The wrapper is offering to Python the illusion that this is a native object. So any operation you do on it is that we actually go and ask the PHP interpreter to do it, and we convert the result back. So that works very well. Now, the problem really is that Python has separate data structures for sequence types and mappings, using the list and the dict. PHP, on the other hand, has just an array. They overload it for both of these purposes. And it shouldn't really be called an array at all, I don't think. It's very confusing. So, when we pass a list from Python to PHP, it makes sense we should get an array with integer keys. When we pass a dict to PHP, we should get an array with mixed keys. What should happen in the opposite direction? Well, it would be nice if we could do something like this, right? If the array has only integer keys, we make it look like a list. If it has mixed keys, we make it look like a dict. Beautifully simple. However, it doesn't work. The reason that it doesn't work is because we can instantiate an array in PHP with integer keys open. We can pass it to Python, so it becomes something that looks like a list, and then we can stash it away in an instance or somewhere. Then later on, the PHP side can then insert a string key into that array. So this is now a list containing an array with string keys. It doesn't make any sense whatsoever. So we have to make a compromise. The compromise is an array will always become a dictionary. If you really want it to behave like a list, you call as list on the wrapper, and then it becomes what Python thinks is a list. However, there has to be a type check here, and with every single operation you then call on this. An exception is raised to say stale list wrapper if at any point the string is inserted, string key is inserted into this. Luckily that's a cheap operation, so it doesn't incur much performance loss. Okay. So at this point I'm happy that we've implemented something which works, but is it fast? So let's begin by defining good performance. So what we want to know is that our composer program, the mix of the two languages, performs similarly to the languages from which it is built, right? Or from the interpreters from which it is built, I should say. So in our case, we want to know that our composer VM runs similarly to Hippie and PyCon. I'm going to say that 3x is too slow. I'm going to aim for 1 to 2x. Obviously, we're going to have some slowdown because of the conversion rate. It's not going to be a free lunch, as it were. This is how we test this. We start with two variants of each benchmark, one in pure PHP, one in pure Python. And then what we do is we take out some of the methods and functions and we replace them by Python ones. Similarly, from variant 2 to variant 4. Okay, so I actually haven't measured variant 4, so the results I'm going to show you are going to be for variant 3 only. And then we use this on a ton of benchmarks. Some of them are the classic computer science benchmarks, other ones are the ones I made up myself. Right, so let's look at some numbers. I apologize for the slide for the numbers. Right, so what you're seeing here is relative times relative to our composed VM running a composed program. And you've got interpreters across the top and benchmarks down the side. Move that pointer up there. There we go. So, for example, running the interchain benchmark, our VM was 22 times faster than CPyCon. Okay? Now, the two interpreters we're interested in are RPython and PyPython. We should be roughly as fast as these two. We'd expect a small slowdown. If you skim down the column, you see we mostly are mostly within 2x. This is slightly slower than 2x, never mind. What's interesting is these two benchmarks here are VMs faster than both of the interpreters from which it was built from. Doesn't make a great deal of sense until you look at the trace. So basically, we speculate we got very lucky with the register allocator here. There's an extra move instruction which is moving, which is basically moving operands into registers. That's true for Hippie and PyPy and not for RPM for some reason. Anyways, it's out of our hands and it's only a small slowdown. In all the other cases, we're well within, we're slower, but we're well within 3x. That's our micro benchmarks. Now for some of our larger benchmarks. And again, the story is pretty much the same, just stimulates down here. We're quite fast at the So yeah, just to summarize, if we take the geometric mean of all of that I've just shown you, what we can say is we're faster than EPVM generally, and we're generally slower than PyPy. And really that's just a commentary on PyPy having more engineering effort spent on optimization. EPVM on the other hand is young, so it hasn't been optimized as well. So overall, I'm happy with the performance. Right, so now we wrap it up, because I'm running out of time. So language boxes offer a practical way of composing language syntax, whilst not giving a horrible editing experience for users. Meta tracing allows us to compose runtimes with little effort whilst retaining good performance. Implementing cross-language behaviors is easy. Designing cross-language behaviors is really hard. In the future, I need to obviously measure that benchmark variant 4. We need a cross-language debugger, desperately. Because whilst we get nice stack traces, we can't interactively debug these programs. I mean, if you attach PDB, it will understand the Python parts, but it knows nothing about the HTML parts. I would like to try a language composition where we have more than 2 languages involved. I'd also like to try a statically typed language to see what happens to performance there. Yes, so I think we leave it there. This screenshot here is something that my colleague wrote. He wrote a plugin to Squirrel now, which is a PHP webmail application, where you can write mathematical formulae in an email, and then it uses SymPy to render the map. Quite cool. And yeah, you see him editing it here. Okay, so that's me done.
Do we have some questions?
Yeah.
I'm wondering how the language box implementation works with like pure text editors, like and GIFs. So GIFs, do they look good?
No. So what happens is the enter saves as gzip JSON. You can version that if you want, but I wouldn't because you're not going to be able to read the diffs, right? So the problem is, this is another facet which we haven't even looked at yet. How do you version these programs? How do you prep them? How do you use all of your standard tools that take a run? And the answer is you probably rewrite. Yeah.
So given that, why don't you just use some token that's totally unpassable in both languages, like
Okay.
5 percentage marks?
What token shall we use?
Unicode.
5 percentage marks altogether.
Okay, I'm going to write a programming language with 5% marks as a pass.
And then you have to say 5 then 5% marks, and then you 5. But it doesn't restrict you to using some weird editor.
This was the alternative, and the guys who wrote, who were dealing with the syntax, I didn't comprehend. The guys who were dealing with the syntax side of things decided that this was a better approach.
What about the add-on sales?
About the,
Add-on sales. The notebook says, not about the notebook.
Yeah.
Yeah.
Oh. What you mean use those as language boxes?
Yes.
Yeah. Why not?
There is after tools in that.
Beaker?
Bigger.
Right. But I mean, would you be able to do cross-language coding and stuff? Probably not, right?
Well, maybe applying what you did.
Yeah, I think we think that. Maybe in the future. Yeah, you should. Yeah.
We can also use sort of a special character in language that just escape. That is a special character that's still
Escaping. I don't like escaping. I'm going to show you something. I'm going to show you some escaping actually. So, what I didn't show you is how these programs become something that VM can consume. This is the random number generator, right? Here. Is that right? Yeah. So this is what you pass to the VM, okay? So you see the compiler method. It encodes the Python function method into a PHP string. It's compiled runtime. We use caches to make sure it doesn't get compiled twice. But anyway, if you embed these things deeper and deeper and deeper, you get exponentially more backslashes to escape. You see what I mean? That's why you really do need this editor. It gets to the point where I can't write test cases without the editor, because I can't embed things more than about 2 or 3 deep without my editor. I don't like to say. Any more questions? Time?
Yeah, I remember it was
For like a minute.
I was got 3 by the way.
Okay.
I was wondering if you could perhaps PHP generate.
PHP generators. Yeah, there's no reason why you can't actually implement it. I mean, I could. There's lots of things I could do. It's just
Generators aren't implemented into the papers.
They were last before they stopped developing. When the money ran out. It was in chunk.
back there.
That's the check. It was a test kit.
You were quick to dismiss using the JVM and the CLR, but those would have, like, you wouldn't have to do any work on the language side because their language is written for the JVM or the CLR, like RPython or JRuby or JPython are using the underlying objects, and so they're already interoperable.
That's true. However, they have to be in separate files, right?
For now, yes. You had to write all this stuff to connect it out of the separate files. I'm just saying, it seems like it would have been a shorter trip, starting with the CLR than starting with PyPython.
Yeah, I mean, I implemented Python and Prolog on top of the JVM, and it was really, really badly. Like, it was the slowest VM quite well.
Yeah, Prolog.
But there are fast Prologs.
There's a Prolog for PyPy that's the fastest Prolog ever.
Yeah, he's not people. The guy that wrote that, you know. Thanks for talking to Gil.
You and everyone else as well.
How would you handle, say, documentation in code? I mean, Python has this wonderful thing for doc strings, and you can parse those as strings, and you create API documentation. But with some functions written in other languages, maybe they don't have the same support for that.
I've been thinking about this problem for approximately 10 seconds. I think it's yeah, I mean, if this works well enough, then you start thinking about that kind of thing. I think it's not the most important stage. But yeah, we probably need that.
Got time for one more.
Yeah.
I actually think this is pretty cool. I would like to do this. Clearly, you've moved things forward a bunch. The question comes, what you said about it's easy to implement all agents, very hard to decide what it should be. And the question is, given that different languages do things differently from a philosophical point of view, we want lists to behave like this, we want arrays to behave like that, we want structures, so on and so forth. Does that, is it kind of a recursive problem that actually you're going to end up with a point where you can't get below because the languages by their very soul decide to split off?
Yeah, that's why you have to make it.
Yeah.
You've got philosophies, open philosophies, just all kinds of things which don't matter. And there's a whole list of things in this field, like dimension, like immutability of arrays, all of these kind of And basically what we have to do is you have to do something which is close to what the user expects, performs well, and is possible. I mean, you're kind of turning into language design at that point rather than language acquisition. I don't really want to think about language design. That's not important. It's in some sense what I'm trying to achieve, but it is at the same time incredibly important because I need it in order to design across languages.
Yeah, non-trivial problem.
Thanks. Thank you.